Hi, I'm Seema Elbash. This is my Module 1 presentation. So I decided to kind of discuss retirement and make that the story of my data. So specifically, when is peak satisfaction of being retired? Most of us look forward to being retired and feel like it'd be kind of nice to know how those who are already experiencing it are feeling about it. So the data set that was given to us, we had 10 X columns, a column differentiating male versus female, and then a Y column. So for the variables, for the X was measuring satisfaction rate in the different in different places within the United States, and then Y is when that peak satisfaction is in years. So we're looking at 5 years being the average. So that'll be like our zero. Next, we have histograms. So I went ahead and plotted a frequency and a density histogram. And I know these look the same, but I just wanted to take a moment to kind of explain the importance and the differences between each plot. So frequency graphs plot the frequency of the data within each bin on the y-axis, and it tends to be kind of easier to interpret for basic data analysis. Whereas a density histogram, this one right here, it has each bar representing the frequency per unit interval in the area under the sorry, yeah. So it's each bar is representing the frequency per unit interval. And then you'll have the area under the curve will always, regardless of the data, will always equal 1. And just an example to kind of make this a little, to make more a little sense, would be, and like to how to look at these graphs would be if I was looking at a frequency graph, I can immediately know what the probability is of getting like X number, for example. But then on a density graph, it would there's a couple stipulations. One, I can't just say, what is the probability of getting 5? It would have to be like, it would have to be a range. So it would have to be, what is the probability of getting like 4.9 to 5.1, basically. And then in order to get that probability, you would have to take the area under the curve within that range. So that's a little bit of the differences between them. But I do want to focus on the density histogram here. I do have a distribution superimposed in purple on the graph showing that it's a mostly normal distribution. Normal distributions are extremely important in statistics. Now, normally the center of a normal distribution is equal to the mean. So you can see here it's kind of off. So that's why I said it's mostly normal. But for the most part, so here, yeah, for the most part, it is taking that shape of a Gaussian curve. So that's kind of why I chose to talk about it. Here we can see that our mean, I wrote it down here on the bottom, mean is 0.11. So it is a little bit to the left of the center of the mean. Um, this here is the mean, and then these two blue lines are just one standard deviation away from the mean in each direction. So standard deviation is the squared root of the variance, and variance is the average squared distance of the mean. So basically, the smaller the standard deviation, the closer all the points will be to the mean. Here we have a standard deviation of 0.75. Now, big thing that's been said in class is that variance is king. So variance is represented usually by sigma squared, and it's the measurement by how far each number is from the data set, how far each number in the data set is from the mean. So while variance is king and that's what's important, it's we tend to keep looking at standard deviation, and that's because it's kind of hard to conceptualize a unit squared, which is what variance is. It's much easier to just look at the unit as it is. For example, like I know I can visualize like 1 foot, right? But then if you ask me like a foot squared, like I would not be able to see that space mapped out in my head. So it's kind of why we look at standard deviation versus variance. I think it's also important to keep in mind that even though we discuss standard deviation more, it does not mean that that's what's important. In the end, variance is what's most important, and I think it's just important to keep that in mind. So up here, I've also attached the outputs for the summary and the describe function within R. I think these functions really help explain the data using our measures of dispersion, and I think it would be helpful to kind of go through some of the important ones and some of the relevant ones here. So here in describe, honestly, I find describe to be a little bit more beneficial, but I think both of them are kind of important. So here, mean is telling us the average. We can always find the mean by adding up all the points in the data and then dividing them by the number of values we have. Okay, next one here is SD. SD is our standard deviation. I spoke a little bit about that before, so I'm not going to touch on it again. Median is our middle value. And then trimmed here is the mean after trimming 10% of the observations at each end of the tail. So this is important because if there's any like outliers, you can take a look and see how the analysis kind of changes after we have them removed, excuse me. So in this data, you can see like here, there's this data point all the way to the end. So I know at first I was looking at it like, oh, is that an outlier? And like I was looking to take it out and see how it affects the mean. But you can actually just take a look here and see that there's a little bit of a difference between, it's not even a serious outlier because the mean and the trimmed mean stayed the same. So it's not an outlier per se. Okay, next one is this min and max. It tells you the smallest and the largest data point, so the minimum and the maximum basically. And I think that's just, it helps you get a sense of like where your data ranges from and see like where your data points fall. And then like along those lines you have range. So like between the minimum and the maximum, what is that range? And then you have skew and kurtosis. So these are talking about the distribution, and it helps if you it helps to tell you if the data is skewed, which direction it's skewed, and by how much. So here you can see we have a skew of 0.08, so we can see it's just slightly positively skewed like we mentioned before. And then lastly, we have this SE right here, which is our standard error. Now this is important because standard error tells us how accurate a sample mean represents the true population mean. So basically that's telling us how our data will reflect in a larger population. And the goal is always to have the smallest standard error as possible, telling us that our data is as precise as possible. Okay. Lastly, I did want to touch on data integrity. I think it's so important to ensure that the that your data that you're collecting, the data that you're reading about, is reliable and verifiable. I think some key things to look at is accuracy. So, is the data correct? Does it match its original source? Are there any missing values? Is the data consistent? Are there discrepancies? Are there conflicting information? And then I think ultimately, like, does the data make sense with what is being said? So I think we just need to kind of pay attention to what we're reading and just make a note of things that kind of don't make sense, and like kind of look into those, because there's so much data thrown at us as consumers every day, and it's a lot. And like a lot of it, for lack of better terms, is garbage. And it's extremely important to know how to distinguish bad data from good data, because you don't want to be looking at like a bad data set that someone presented to you and kind of take that as truth, whereas it can't be taken as truth because the data is not good. So I think that's kind of important. Any questions, let me know. But that's all I have. Thank you.